Okay, welcome. I hope we've enjoyed our session so far. What I'd like us to do is take a look at all the arithmetic we've been doing. We've been doing without what we call we've been doing all the addition, the subtraction, the division, and the multiplication. Now, because the computer precisely can only add, it cannot do anything else. What we do is we have ways of manipulating its addition so that we achieve the multiplication. What do? We complement a number to add it. Let me say what do I mean here. If we say a number x minus, let's say, another number, let's just call it s. X minus s would give us what? What we're doing is actually we're subtracting, right? But in our subtraction, what we do, because the computer cannot subtract, what we do is that we then manipulate our number through what is called complementing, and we complement. This simply says the complement. So actually x minus s can actually be achieved by what? By the addition of the complement. Instead of subtracting the number, I can actually achieve that subtraction through adding its complement. So basically what we are trying to do here is we're trying to understand complements, to understand with this complement. So before we can do the actual arithmetic, the subtraction via addition, we need to understand what these complements are. So for a number, let's say we are already talking about the x. We are going to come to codes later and say when codes are self-complementing, what does it mean? Complementing simply means that if you're complementing, let's say you're complementing a person, what you're trying to do, you try to add onto their sense of what? Sense of self. You're trying to boost their self-esteem. So complementing is basically boosting. So if we're going to say now we are talking of decimal complements, let's talk about the decimal complements. We have what I'll call the base complement, which is the tens complement, and we've got nines complement. All right, it is easy to actually understand what the nines complement first. So let's do this. Let's take a number. Let's take the 0, the 1, 2, 3, and 4. I'll end here because complements are back to back. I'll show what I mean by in a second. The nines complement is what would actually fill up this number to a 9. Obviously, it's the 9 itself. All right, what I would need to add to that number to get a 9. The 9's complement of 1 is therefore 8, because 8 and 1 would give us what? Would give us 9. Now, the 9's complement of 2 would give us 7. Why? 2 and 7 give us 9. The 9's complement of 3 will therefore be 6, because for obvious reasons now. And it goes without saying that the 9's complement for 4 will be 5. Why didn't I continue? Because from that point on, it's back to back now. That 5's complement, the 9's complement of 5 is 4. The 9's complement of 6 is 3. The 9's complement of what? So what I'm basically trying to prove is that complements are actually back to back. So if one number 9 in this first example, if one number is another number's complement 0, then that number is also the first number's 9's complement. So complements are actually back to back. All right, so it's easy. If I had a number, let's say more than one digit, let's start with 2 digits, and I want 9's complement of that. These are the numbers that will make that number 99. That will convert that number into a series of 9s. In this case, 2 digits, 2 digits of 9, two 9s. If I had 345, these are 3 digits. This is the number that would actually what? Take us up to 3 9s. If I had 4, it goes without saying, it will be 4. So every number, the number of digits of the number of digits of a number's complement is the same as that number's digits. It's on digits. Okay, so if you look at this now, what will take us to 99? It will be an 8 here, an 8 here, and a 7 there. Therefore, the 9's complement of 12 is 87. What will take us to a set of 9s with the 345 here is going to be what? It's going to be the 6, 5, 4. 4. So basically it's putting together the individual digits, nines complements. Okay, so you can see the nines complement of 3 is a 6, the next complement of a 4 is a 5, the next complement of a 5 is a 4, and therefore it is basically putting together that if there's more than one digit, it is basically putting together those nines complements in such a fashion that if you were adding the two complements, your result will be what? Will be a stream of nines. All right, nines complement is very easy. Let's go and take tens complement. Tens complement is simply equal to nines complement plus 1. Nines complement plus 1. Okay, so what am I saying here? I'm simply saying then if I take the same 0, 1, 2, 3, 4, and I want a tens complement instead, this would have been 9 plus 1. But we don't worry about the carry, we only worry about the sign. So tens complement also be a 0 because it would have been 10, but this is a carry. This we consider this a carry. We don't include it. We just worry about the sum. Okay, so our sum here would have been 0. If you added the two together, our sum would have been 0. That would have been the carry. So we only worry about the sum. So I will remove that. Okay, and then if you look at the next one there, remember this is what? 9 plus 1, which was 9's complement plus 1. All right, if you look at the 10's complement of the second one of the 1 is now, that one was an 8, this would be a 9. Why? This was 8, again it's 8 plus 1. So all you see here is this was 9's complement plus 1. If I go on and say let me rather do this, let me say 9's complement plus 1. So all of them will be 9's complement plus 1. So here it would have been an 8. The 9's complement is an 8. 8 plus 1 is 9. If you look at the 10's complement of 2, that is what? 9's complement would have been a 7. 7 plus 1 is an 8. Obviously, it goes without saying that this will be 7 and this will be 6. All these are 10's complement. All right. So obviously, going back, if you're going to say now the 5s, if I have a 5, the 10's complement will be another 5. Okay. Now, if you look here, that is what? 9's complement would have been a 4. 4 plus 1 is a 5. So, going forward, it's going to be what? It's going to be back to back as well. So what it means is, if a number, take the 6 for instance, if a number is another number's 10's complement, that number is also what? That number is, the first number is also what? 10's complement of the second number. So basically, complements are what? Are back to back. So these are what? These are the ternary, or I've been dealing so far with the what? With the ternary or best 10 complements. Okay, decimal complements, which is also called what? Our best here is obviously 10. All right. So this applies to, but just remember that if we have a number, okay, and we want to subtract that, where do we use these complements? We want to subtract a number. What we'll do is we can add the complement of what? Of the I didn't do an example of what? Of 12, for instance. Let's take 12. The rule says 10's complement is 9's complement plus 1. What was 12's complement, 9's complement of what? Of 12, it was 87. If we follow the rule, therefore, our answer is going to be 88. Okay, let's take 345. Our rule said this is 9's complement. 9's complement plus 1 makes this 655, because the previous one was 654. 64 plus 1 is 655. Let's see what's interesting here. We said if we take a number and add it to its complement, we are going to get a stream of 9's. So 7 plus what? Plus 2 is a 9. If we add a number to its own 9's complement, we are going to get a stream of 9's. 8 plus 1 is a 9. Let's come to this one here. Let's take 654. Maybe I should come down a bit. Okay, maybe I should come down a bit. If we take 654, which is 9's complement of what, of 345, if we add the two together, if we are correct, our answer is a stream of 9's. 4 plus 5 is 9, 5 plus 4 is 9, 6 plus 3 is 9. Okay, let's see if the same works for what? For 10's complement. Now with 10's complement, if we take that complement and we add it, we must get what looks like a stream of 10's, if you are correct. Let's look at this. 8 plus 2, it is a 10. Of course, we write the what? The 0, and we what? We carry the 1. Now it's 8 plus 1 plus 1, it would have been a 10, and what we write? We write the what? The answer there, 0, is going to give us a stream of zeros. But of course, the final carry will always be a 1, because each time our sum would have been actually a 10. Let's try that with the second example, 655. If we are correct, we're adding. If we add a number to its complement, the rule must follow that the answer must always be the what? The complement that we're talking about. So we're having 10 as our complement here. 5 plus 5 is 10. Of course, we put down the 0 and we carry. That's mathematically legit. Now, again here, 5 plus 4 plus 1 is 10. So our answer is 10 all the time. And then, however, the rule says we write the what? The sum, and we carry the 1. Now that there is what? You can see it would have been 10. 6 plus 3 is 9 plus 1, 10. So it's all 10s. That would be the case with every scenario in the what? In the no matter how long the numbers were. So now we'll write a 0. You can see our answer looks like a what? But looks like a set of zeros, but it's because each time we are carrying the 1 that makes it the 10. Okay, so 9's complement and 10's complement, basically the difference is what? You just add 1 to the what? To the 9's complement. Now, if we go and say, what about the other, let me rather say another page. What about if we have the binary complements? Would that still apply? Remember, why do we do complements in the first place? It's because when our computer cannot subtract the number, the complement makes us able to instead add the complement. Okay, so a number, the difference between two numbers is actually the one number plus the what? Let me rather say the subtrahend. The subtrahend, because the one that you are subtracting, we can actually add its complement. All right, so now remember this is the whole reason why we're doing this. So now let's go to what? The binary or base 2 complements. Binary or base 2 complements. All right, so obviously here we have the 2's complement and the 1's complement. I will again start with the 1's complement because it's easy. Let's take the number 0. There's only 2 digits in what? I don't even know why I bother. I actually want to show you I don't have to bother with this one. Why? Because they are back to back. There's 0 and 1 here. The 1's complement of 0 is a 1. If a number is what? If a number is a complement of another, that number is also its complement in the same what? In the same base. So if our base of complementing is 2, it means that the what? The 2's complement of the one number. If one number is the complement of another, then the other number is also complement of our number. So now it means therefore for 1's complement, 0 is also what? 0 is 1's complement of 1. If 1 is 1's complement of 0, then 0 is also what? 1's complement of 1. So the complementing is what? It's actually nice and easy. It's back to back. What about the 2's complement? 2's complement follows what you did with 10's complement. We said 10's complement was 9's complement plus 1. In this case, 1's complement plus 1. Okay, so the same rule that we had with the base complement. The base complement is always the base minus 1's complement plus 1. So now if you look at 2's complement, let's take the 2, 0 and 1. The 2's complement of 0 is going to be what? It's going to be 0 because it must add up to give us 2, but we are going to carry that, so we don't show the carry, we worry about the sum, and therefore our 2's complement of what? Of that is a 0. All right, the 1's complement of what? 1's complement of 1 was a 0. 2's complement of 1 is 0 plus 1, which is a 1. Okay, so what does this mean? Let's take a longer number. Let's say we have 1 0 1. Let me say 1 0 1 1. We want the 1's complement. You can see all the zeros will change to 1s, all the 1s will change to 0s. Okay, we go the other way and the other way. So this here is going to be 0. I cannot drop it to show that it was actually 4 digits. It was a 4-digit number. That's a 1. That's a what? That's a 0. That's a 0. Okay, is it correct to drop this 0? Like normally would exclude, with a normal number would exclude this 0. Is it correct to do so? No. Why? Because then you don't know whether you're having, if you drop this number, if you drop the 0, let's suppose you should not write 1 0 0, because then it would give a fake impression that your original number was what? Because this is going to be 0 1 1. It would give a fake impression that the original number was actually a 3-digit number, 0 1 1. Whereas our original number was what? Was 1 0 1 1. So it's not okay to drop the what? The complement. Okay, to drop the 0. You cannot do that. So what you then do is you try and do 2's complement. We know that 2's complement is going to be 2's complement of the same number is going to be that one there plus 1, which is 1 0 1 0. This is 2's complement of what? Of that number there. Now if I take another example, let's say I have 1 0 0 1 0, and then you say, okay, let's get 1's complement of that. 1's complement will be all the 1s will change to 0s and the 0s will change to 1s. So we would have something like this. Now when you have something like that, again, remember you can't drop that. So now what does it mean? 2's complement is simply that plus 1. 1's complement plus 1. This will be our 2's complement. It will be 2. The other ones stay the same. So if you look at that, if you look at 2's complement, I want you to notice something very important here. Okay, I want you to notice something very important. If you look at the original number, if you look at our number, you can see up to that 1, the number stayed the same. Coming from the right, up to the first 1, the number stays the same. The rest is 1's complement of the original number. So this was 1 0 1, that's 0 1 0, but our first one stayed the same. Let's look at this here. 1 0 0 1. So the number stayed the same up to what? Up to the least significant 1. Okay, the number stays the same up to the least significant 1. All right, and then you do, if you look at now, that 1 0 0 is 0 1 1, but it was 0 1 0 1. That part didn't change. What changed was the rest. It became 1's complement. So what you can also say is, you must notice that if I took a number like, let's say now I took a number like, let me move this to the side a little, and no, move the whole thing to the side a little bit. Okay, let's take 2 examples. I will take a very long number. I will say 1 0 1 1 0. I can even put commas. Does it change? The complement does not change. The what? Let me say now, I'm not very happy with putting useless zeros, because zeros after a number are actually what? Are actually redundant. So I want to be very practical in this case. So I will exclude or I should have just removed the comma. So what I want to point out is, if I had zeros here without a comma, those zeros cannot be dropped. So they're not redundant. So now if I look at this now, if I want to do the 2's complement of this number, I can go straight up to it. I'll do this 2's complement. I'll go straight up to the 2's complement. I know the number will stay as is up from the right up to the least significant what? 1. So the number will stay as is up to the least significant 1. Then I can do 1's complement of the rest. If I look at that, it's 101. 1's complement is be 0, 1, 0. Okay, let's see if that's true. 1's complement will say every 1 to a 0, 0, 1, double 0, and triple 1. Am I right? Okay, I just didn't make it open it up. Right, let me try to do that. I want to be clear with the things that I do. Let's try and clear that up. I want to align my numbers. So I want to say this would have been 0, 1. I'm trying to line it up. 0, 0, triple 1, 1, 1, 1. And if you said, okay, that's 1's complement. When you change every 0 to a 1 and every 1 to a 0, that's 1's complement. Let's see if we add 1, we're going to get that. If you are correct, I'm saying I've done this previously. I've said I'm adding 1 and somehow I've put a C. Okay, so now if we add the 1, 1 plus 1, 0 carry 1, 1 plus 1, 0 carry 1, 1 plus 1, 0 carry 1, 1 plus 0, 1. Then 0 plus nothing. Can you see? So it works out fine. This is our what? This will have been our sum 4. Now let's try another one. Let's say we have 1 0 1 0 0 1 0 1 0 0 0 0. Okay, now I'll do 1's complement, then I'll do 2's complement, but I'll start with the 2's complement to prove our theory. So I'm saying our number stays as is for the 2's complement from the right up to the what? Up to the least significant 1. So we've got 1, 1, 2, 3, 4. There's 4 of them. And then the rest changes. That's a 1. That's a 1, right? That's 0. That's 2 1s. That's a 0. That's a 1 and a 0. Okay, so let's see if it's true. So our number, again, our number stayed the same. 1 2 3 4 zeros. 1 2 3 4 zeros. The fifth one, that was the first one, so the number stayed the same. It did not change them. What changed was everything else was what? Was toggled over. So let's see if that's true. Let's take our let's say we're done our 1's complement would have changed every 1 to a 0. That's 0. That's 1. That's 0. That's 2 1s. That's 0. That's 1. That's 0. That is 4 1s. 1, 2, 3, 4. Then when we to prove, we should add 1 and see if we're going to get what we predicted. 1 plus 1 0 carry 1. 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 1 with nothing 1. Then the rest is the same 1 0 1 1 0 1 0. So our method works fine. So with 2's complement, you can just look at the number from what? From the right up to the least significant 1. The number stays the same up to that point. Then all you do is 1's complement of the rest. But otherwise, don't get lost between the language, the jargon. What you can do is simply do 1's complement and what? And add 1. Now, what if the number had commas? If the number had commas, even with the what? Even let's start with the decimal. Let's say our decimal had what? Has a number with commas. Does it matter? Let's say we have got 2.37 and you are required, let's say 12.37, and you are required to do 9's or 10's complement of that. All that you do is what? It's very important to note this though. The comma stays where it was. This here is going to be 9's complement of the number as if there was no comma. That would be an 8. That would be a 7. That would be what? A 6. And that would be a 2. Alright? Then what you then do is, you say that's 9's complement, the comma stays in its place. So it does not affect the comma. You just complement as if there was no comma. Just keep the comma in its place. So if we were doing 10's complement, you will add 1. Are you adding 1? You are adding to the list. You add as if there was no comma. So you would go and say 8, 7, 6, 3. I've added to my number. I've added my 1 to the number as if there's no commas, but the comma stays in its place. Okay. So we're not really adding a 1 as such. We're adding what? We're adding a 1 bit. We're adding a 1 bit to the least significant digit. So if I was adding 1, that's going to be 8, 8. I'm going to have to change that to an 8 because that's where 1 would have come to add onto the what? onto the units side. So when you're doing what? When you're doing the complementing, you don't care about the position of the comma. You do the complementing as if there's no comma, but you remember to put the comma back in its what? In its place. If the number was something like a binary number, in a binary case, if the number was 101, 1101, for instance, and you are required to do one's complement of that, you do the complementing as if there's no commas. That would be 010, another two zeros, and then 10. So we did the complementing as if there were no commas. All you do is come and put the comma in what? In its place. There were 4 decimal places, you put it in its place. Okay, so the complementing does not affect the what? The comma. If we're doing 2's complement, we know that 2's complement is what? Is supposedly 1's complement plus 1. But is it entirely true? No, we are adding the bit 1, the same that we did with what? With the 10's complement. What we do is we do the number stays the same up to the first one. So the first one is the first one. The rest is what? Is 1's complement. So it will be 1, 0, 0, 0, 1, and 0. So what you do is you put the comma back in its place. There were 4 decimal. Oh, not decimal. This is not. Remember, these are decimal. This is a decimal point. This is a decimal point. But because we are working with decimal here, this cannot be called a decimal point. This is not decimal. So what is it here? Is it a binary point? Maybe you could call it a binary point, but we rather call it a radix point, because even that is a radix point. Okay, so radix is universal, but decimal speaks to decimal numbers. This radix is for any other system, even if you're using the octal or whatever. A radix simply means a comma. Okay, a comma in any base we call it what? A radix. So it's not exactly correct for me to say I'll put the decimal point in its position, I'll put the radix point in its position. There were 4 places after the radix point, so I'll put my what? I'll still count 4 and put my radix point. Okay, so I hope I clarified matters. I hope I didn't complicate issues, but basically it was me introducing the what? The complements. So that when we come now to what? To doing, remember what we're doing it for. We're doing it to be able to achieve subtraction via addition. Our computers, yes, we can say we have a subtractor in a computer, but what has the computer done? It will basically complement a number and add it. Okay, you will see it will use an adder. Okay, that subtractor is actually an adder with a what? With a complementer. Okay, with some complementing. All right. So what have we achieved? Basically, we now know how to do our in our next sessions. We're now going to deal with what? With the individual. We are going to do this mathematics now. We're going to do the arithmetic using complements. Thank you. I hope you enjoyed that. I hope that was informative. I hope I did not babble a lot. I didn't make too many mistakes. Enjoy yourself. Let's meet again when you to come back with the arithmetic.